Some of you are probably a bit fed up with the sight of me again, well, you just have to put up with it for at least an hour and a half. My name is Jonathan Rambo. I'm president of EGU, but in a previous life, I was actually a researcher at something called Department of Space and Climate Physics of University College London. That still builds actually a lot of instruments for ESA missions, so I'm also an Earth observation scientist. This is Union Session 2, although it's actually the first of a number of Union sessions, and you have got you've got 6 really fantastic speakers talking about, well, the title of the session is Future of Earth and Planetary Observations from Space. And the first half will be looking down on the Earth, and the second half is looking elsewhere in the solar system and beyond. Our first speaker is Mike Freelig, who is head of Earth Sciences at NASA. Is that, yeah, about right, for the last 11 years, I think, something like that. And he is going to talk about looking down on the Earth, satellite science and societal benefit. And I should say that you've got, if you want, you can have a second treat tomorrow, because he is also going to talk in another Union session on the contribution of satellites to the Geosciences in general in the past and their future contribution in another Union session.
So how does this work? Sorry, I'm just trying to figure out how to advance the slides here.
It's the left-hand button. Just if you click the left-hand button, and then
got it.
Going back is tougher. Yeah.
We don't go back in this field. We only go forward.
Yeah.
Damn the torpedoes, full speed ahead. And thanks very much, and it's an honor, as always, to be speaking with good friends, old colleagues here at EGU. And perhaps the title of the talk is a bit switched with yesterday, because I have to tell you that I'm not going to be showing a lot of pictures or hardly any results whatsoever today, but we will at the Union session tomorrow, the so-called US1 session. What I'd like to do today is to provide you with a programmatic update on the NASA Earth Science Division, where we stand and where we're going in the next couple of years, with a particular emphasis on the next year. So in the talk today, I know that there's been a lot of questions and concerns about the budget for NASA and for Earth Sciences in the US in particular. I'll give you some good news on that. Spend a fair amount of time going over our research flight missions and the overview and our plans for the next several years or so. We've just had a decadal survey that I think many of you are aware of, and it's quite a substantial path forward for us into the next decade and through the next decade. And we'll go over with you our plans and mostly our approaches for that. Talk a lot about partnerships, because indeed the decadal survey was specifically focused, was explicitly focused in part on partnerships. And if time remains, we'll talk about the research, the technology, and the applications portions of the Earth Science program at NASA. So, in terms of the budget, a lot of words on a couple of charts, but the basic point that I would like to make is that notwithstanding all of the Sturm und Drang that people may have heard over the past year or so, in the final appropriation, the final budget that NASA received, Earth Sciences at NASA continues to be funded for the rest of this fiscal year, at the least, at the same high level that we have been funded in the past 2 years. That is sufficient funding to do everything that we had planned, just about everything, that we had planned. And so, and it is, by the way, the level at which we had been spending in the first half of this fiscal year. In the US, the fiscal year runs from October 1st through September 30th. And so the new budget that we have is at a high level, and it does not require us to perturb our plans at all. In particular, there was talk in the President's budget proposal for the US fiscal year 2018 of terminating development of several missions, and those have not been terminated. Okay, and they're listed up there. We did discontinue a mission, the Radiation Budget Instrument. We more or less temporarily discontinued it because of technical problems, schedule problems, and cost problems, but we're working on mitigations for that. So again, the word is, from a budgetary standpoint, that our budget remains at the same level of the previous years. And so this is the typical chart that we show for the NASA research missions. This is not all of the US Earth observation missions, because it does not show any of the NOAA operational meteorological satellites. Rather, these are our NASA research missions, many in conjunction with interagency and international partners. The bottom portion of the chart with mission names in green and that teal color blue are our presently on-orbit missions, and the dates associated with them are the earliest possible date that we think, for technical reasons, the mission might end. The upper portion of the chart, where the names mission names are in, yeah, I guess you can see that, are in this sort of orangey or yellow type, are missions which are approved and are under development for launch between now and 2022 or 2023 at the outside. We're presently flying about 16 missions and major instruments, depending on how you want to count them, and we have about 19 missions that are under development for launch between our very next launch, which is going to be Grace Follow-On, launching on the 19th or the 20th of May, joint with GFZ in Germany, and all the way up through Landsat 9, Sentinel 6A, that we're in coordination and collaboration with European Space Agency and the European Commission and several others. What you see here is that we have a research fleet which is making measurements of many different variables in many different ways. Some small satellites which are focused on a single variable, some large multi-instrument satellites. The objective, of course, is to have a portfolio of missions and a fleet of satellite measurements which measure many different variables all at the same time, so that we can understand the connections and the interactions between processes and not simply the individual processes that are taking place on Earth. Basically, our objective in the Earth Science Division is twofold. The first one is to understand the Earth as an integrated system, and the second one is to take the measurements and the understanding and turn it into societal benefit to improve the lives of each and every human on this Earth. We're using a variety of different platforms, as I mentioned, including instruments on the International Space Station, and as you see on the right here, a rather broad group of CubeSats and small sats for technology and for science as well, and I'll talk about that coming up. Without going through in exquisite detail, I just want to show you the many, many notable events in the last 6 or 7 months and the upcoming few months. We have ended a number of missions like the GRACE mission after many, many years, the Cloud Aerosol Transport System mission, an old instrument, the Thermal Emission Spectrometer on the Aura spacecraft, and one that's close to my heart, QuickScat's finally going to be turned off at the end of this fiscal year. I mentioned that we're discontinuing the radiation budget instrument, but we are looking at alternatives to provide measurements for Earth radiation budget with launch dates in around 2026. We've taken a couple of old missions and moved them out of very high value orbits, such as JASON-2 OSTM, moved slightly out of the nadir altimeter orbit in order to preserve that orbit as the mission itself gets old and redundancy moves away. CloudSat, which flew in the A train, has been moved successfully just below the A train. Those missions continue to provide high-quality measurements. And we've done several launches. The TSIS-1 for total solar and spectrally resolved solar insolation measurements was successfully launched to the ISS, the International Space Station, and it's presently operating. NASA, working with NOAA, NOAA funded it, launched the JPSS-1 operational meteorological mission, which also has things like the ozone, total ozone measurement system on it, and a number of CubeSats. That was all in the last several months. Going forward, we will be completing the Orbiting Carbon Observatory 3 mission and launching it late in this calendar year or very early next year, depending on when we can get it to the International Space Station. GRACE follow-on I mentioned is on track for launch in May 19th and 20th. ICESat-2 is on track for launch in mid-September of this year. EcoStress, thermal emission measurements, hyperspectral, or multi-channel, I should say, was shipped to Kennedy, and it's on track for launch to the ISS at the end of June. Vegetation Canopy LiDAR, JEDI, its delivery has actually been accelerated, and it will be flying to the ISS perhaps as early as November. In just a couple of days, on May 20th, from the East Coast, a set of technology demonstration CubeSats will be launched, with others coming, and we've made some selections in our Earth Venture competitive program, a hyperspectral mineralogy mapper and detailed hyperspectral measurements of far infrared emissions in the Arctic. So a very busy program that we have in just the next several months, not to mention the next several years, and we have the funding to do it. We continue to push the envelope forward in terms of innovation in system design. And last year, I talked about each of these in detail. I will simply point out that we continue to examine advanced ways of making instruments. Heterogeneous constellations, like the A-Train, providing far more capability in a virtual observatory than one could ever get from a single satellite. Semi-homogeneous or semi-heterogeneous constellations, like the Global Precipitation Measurement constellation, in which we fly in a core observatory joint between NASA and the Japanese Space Agency, JAXA, and we use that observatory to calibrate and characterize instruments from many different other programs, each of which have some relationship with and provide information about precipitation. And then we combine them all together for the first time to be able to look rapidly and at high spatial resolution at precipitation over the entire Earth. We have homogeneous constellations like Cygnus, which is flying now, Tropics, which will fly, in which we have the same spacecraft flying in formation in order that the payloads are exactly the same, in order to get increased temporal frequency, especially for atmospheric-related phenomena in the tropics. You saw that we're using the space station, and we are exploring with a number of different instruments, hosted payloads on commercial geostationary satellites. We also have a hosted payload on a low Earth orbiting satellite in Maya. Our competitive venture class program is moving forward. It's fully funded. It's on schedule. We just made announcements for our 4th Earth Venture instruments, and I mentioned those: EMIT, the hyperspectral mineralogy mapper, and PREFIRE, the far infrared measurements in the Arctic, and we have more solicitations yet to come. On schedule. We are exploring using small satellite, CubeSat, and private sector technology to advance our research aims. And I have about 4 slides on that right here. First of all, we're using small satellite technology for science with Cygnus, with tropics, and for in-space validation. Those were the ones sort of on the right-hand side of the fleet chart that I showed before. We're actually investing. I invested some science money in small launch vehicles so that we will hopefully have an industry that provides for, say, $15 million per launch, the ability to put at least a CubeSat, but generally far more capable spacecraft into low Earth orbit. This is important if you're going to build constellations where the components of the constellation have to fly in particular orbits at particular times. You can't just launch as a secondary and hope that somebody else is going to go to the place that you want to go and at the time that you want to go there. There are many different funding opportunities that we make available for small satellite and CubeSat solutions. I particularly want to point out the one down here and say a few words about it. We are embarked on a pilot project to evaluate the utility of observations from private sector small satellite constellations that were launched for other reasons, but to evaluate to determine the value of those measurements for advancing our research program. This is a different way of NASA and perhaps a different way of any space agency of dealing with the private sector. Because what we are doing is not saying we are looking for private sector solutions that have these particular characteristics. Rather, we're going to the private sector and saying, if you are flying a small satellite constellation that is observing the Earth, we would like to evaluate its utility for our research purposes, and so then we will buy, if we can come to some appropriate agreement with you, then we will buy your data rather than complementary with, not necessarily instead of, flying our own spacecraft to make those measurements. Again, this is a different way of looking at things, because we're not saying you must provide data of this particular quality of these particular variables. Rather, we're saying, since you're providing that data already, we'd like to see how much it's worth to us, and then we'll buy it from you. We are not funding industry to put up the constellations. Rather, we are providing, we're buying their data for constellations that they've already put up for their own reasons. And this is going along in a very rapidly evolving field very well. We have money right now. We are in the process of establishing contracts with 4 different private sector firms And the point here is these contracts are for one-year pilot evaluations. We will get the data in from them, and then we will give it to a broad range of NASA Earth science researchers for them to provide the evaluation for the quality and utility of the data. The quality of the geophysical information, we will be working with the companies to try and determine the price sensitivity of things like latency and the ability to sub-distribute freely and openly, and we'll be evaluating the supplier plans for long-term measurements. The hope is that coming from this, we will be able to establish a stream of private sector measurements for our Earth observations to complement the measurements that are in our program of record. I'd like to say a few words about the Decadal Survey. And I'll go through it pretty quickly because I'm fairly certain that each and every one of you in the audience has read that 700-page document many times. You're laughing. No, this is no laughing matter. So, as you know, in the US, the National Academies of Science release or provide decadal surveys once every 10 years. It's funny how that happens. That for NASA, at least, define the entire scope of the Earth, or comment on the entire scope of the Earth science program. Distilling the 700-page document into just 2 slides, fundamentally what they said was, do that fleet plan that was shown on the one picture that I showed you before. Do it on budget, and do it on time. Okay? So they did not ask us to perturb the plans that we already had and get all of those missions flown before the midpoint of the decade, before 2023. Okay? And then they gave us a lot of leeway in terms of how to make some other key observations. They did not define missions, but rather they defined science problems and key observations, giving us in NASA the flexibility for figuring out how to translate from observations to missions, and recognizing explicitly that the Earth science gets done from the portfolio of available assets, and not simply science from this mission, science from that mission. But we have to combine the data from many missions and from partner missions. The Decadal explicitly noted the value of and encouraged international partnerships. What they did was to tell us to make acquisitions in 5 designated observable areas: aerosols, clouds, convection, and precipitation; mass change, red gravity; surface biology and geology, red hyperspectral surface; and surface deformation and change, red synthetic aperture radar. Okay? A lot of details here that I won't go through, but they were very cost conscious and told us to be cost conscious. They told us to introduce a new middle range of competed program called Explorer, not as low cost as the $150 million venture class that we've had and that I talked about before, not as large as the $805 or $650 million designated missions. Definitively competed. And they asked NASA for the first time to examine approaches for demonstrating the ability to make long-term measurements of particular variables in a programmatically sustainable and realistic way. Venture class continuity. Not that NASA should make those measurements, but rather that NASA should demonstrate with technological advancements and spaceflight that such measurements could be made, either by us in the future, by other agencies, or perhaps turned over to industry. And we're in the process for the next 18 months or thereabouts to translate these large-scale strategic directions into specific missions. I want to say a word or two in the 3 minutes remaining here about partnerships. Partnerships were key in the recommendations of the Decadal Survey. You know that we in NASA have partnered both domestically and internationally over the previous decades, and we will continue to do that into the future. For our currently operating missions, you can see here all of the partnerships, or many of the partnerships actually, that we have for the missions that are flying now. Partnerships with individual European space agencies, partnerships with the European Space Agency, partnerships with other international space agencies such as JAXA and ISRO and others. Partnerships with the Canadian Space Agency has been a stalwart partner of us in many aspects, and partnerships with NOAA and the USGS. Looking at our missions that are presently in development, you can see that GRACE follow-on with GFZ, Sentinel-6, nadir altimetry with ESA, EUMETSAT, NOAA, and the EC is involved. Partnerships in our Landsat series with the US Geological Survey. Partnership in wide swath altimetry with our surface water ocean topography, hydrology, and wide swath altimeter mission with the French Space Agency, the Canadian Space Agency, and the UK Space Agency, and partnerships with our major L-band, S-band L-band, S-band synthetic aperture radar mission with the Indian Space Research Organization. So we have been committed to partnerships, and we continue to be committed to partnerships. And let me just end on this slide, but I can take questions on other parts of it. Remember, I pointed out at the very beginning that the objectives of the Earth Science Division at NASA were twofold: to understand the Earth as an integrated system, and to turn that understanding and the unique vantage point of the measurements, the unique vantage point of space provides into societal benefit. Sort of nothing there said fly satellites, okay? So we have 4 basic elements in the program. The flight element that we just spent a lot of time talking about. The research and analysis element, which integrates measurements and understanding from many different sources, not just NASA spaceborne missions, not just US spaceborne missions, but airborne, et cetera. The RNA program addresses science problems, understanding the Earth as an integrated system. The Applied Sciences program takes that understanding and demonstrates its utility in terms of providing efficient information products to decision makers of all sorts. And underlying it all is our technology development program, where the objective is to invest in developing technologies today so that they're available at a relatively mature level for use in designs of future measurement systems, as opposed to choosing a mission and doing the technology development that's required in the context of a mission, which, as Joseph and others can testify, and we've done the same thing, turns out to be a rather expensive proposition if the technologies don't get developed right on time. So this is the scope of the Earth Science Division program at NASA. I hope I've given you a little bit of insight into where we're going in the next couple of years. And tomorrow in the union session, I'll be happy to talk about some challenges, but also some accomplishments in the geosciences from our program. Thank you very much.
Yeah, no. We have time for questions for Mike. I mean, there was an awful lot to chew on there. So, I mean, yeah.
National security satellites and constellations of national security satellites in the U.S. have capabilities that I believe will contribute significantly to studying your system. Would you extend the private sector pilot to include data from those kinds of constellations?
Can you just briefly repeat the question?
Yeah. Was an excellent one, and that is national security satellite systems in the U.S. Also observe the very same planet and might possibly have their measurements may have some value, and would we extend the pilot program to them? And the answer is, in concept, yes. We are already working with the National Geospatial Agency to sanitize and appropriately transfer relevant measurements, a large quantity of relevant measurements, and this has been going on for some time. The key objective of the small satellite, private sector small satellite constellation is to learn how to work between NASA and the private sector, not necessarily the other parts of the government. But with this administration in the United States and with the strong understanding and, frankly, credibility that has been built on both sides, both in the intelligence community and at NASA, we continue to explore every opportunity for getting information for research needs that will help to strengthen the nation and in ways that will not infringe on the particular aspects of security that some of those systems were flown for. So that's a long way of saying yes.
Time for one quick question, if someone has got one. If not, yeah, okay, Margaret, yeah, go on.
Could you comment on why the radiation budget measurement will be discontinued? You mentioned it in your earlier slide.
Yeah. So real quickly, the objective of the measurement had been to continue into the future the series measurements, CERES, measurements that have been taking, that we've been taking ever since TRIM launched in 1997. And it just turned out that the design that we had chosen and the implementation approach that was being used was running into dramatic cost, technical, and some schedule issues. And so in order to complete that instrument would have required a significant perturbation to the rest of our program. And given that the last of the series instruments just launched in November on the JPSS-1 satellite, and we have several more that are in orbit as well, we felt that it was better to step back and actually look at a more programmatically achievable and realistic way of making those measurements in the long term, in the future. So it has nothing to do with the measurements themselves, it's building the instrument.
Brilliant. All right, thanks for that, Mike. I should say that you will have a chance to grill him at length tomorrow in Union Session 1 on grand challenges in Geosciences and so on. The next speaker is Xiaolong Dong, and he is a professor at the National Space Science Center in Beijing, and we're very fortunate to have him here to speak to us today about research and operational satellite programs for Earth science and applications from space in China.
Okay.
Thank you very much.
Good afternoon. I'm going to report to the overview introduction to the Chinese space, the Earth observation missions for both science and applications. In China, there's no distinctive differences between the research missions and the operational missions, so that's why I gave an overall introduction. So this presentation is Yes, with the contributions from several of my colleagues from the different operational agencies. They are the Professor Peng Zhang from the National Satellite Meteorological Center of the CMA, and Dr. Ming-Sin Lin from the National Satellite Oceanic Application Service of the State Ocean Administration, and also Dr. Xu Huichen from the Center for Earthquake Observation from Space, the China Earthquake Administrations. So this is an introduction to the Chinese, the National Earth Observation Satellite Systems. So in October of 2015, the Chinese government approved an overall program. That's a Civil Space Infrastructure Program of China. So this program have included the Earth observations and also the navigations, the telecommunications, broadcasting. So for the Earth observation satellites, so there are 3 series under this program. So that's the land series, the ocean series, and the atmospheric series. So for these 3 series, so 7 constellations were planned. So that's for the land imaging. So we have the high-resolution optical imaging constellation and the mid-resolution optical constellations, and also the synthetic opto-radar constellations for both the low orbit and the geostationary orbit. And for the ocean constellations series, we have 2 constellations. That's the watercolor constellation and the ocean dynamic constellation. And for the atmosphere, so we have the Leo meteorological constellation and the Geo meteorological constellations. And in addition to these 7 constellations, we also have 3 specific satellite series. One is the ocean environment surveillance satellite, including the radar and also the geo imagers. And the second specific series is a physical field satellite, including the electromagnetic field and also the gravity field. And the third one is the atmospheric composition satellite. So that's the overall of the several observation. But for this presentation, I only focus on 2 of the series. So that's the ocean series and the atmosphere series, and also the one of the field, the physical field satellite. That's the electromagnetic field. So that's the content for this report. So for the meteorological satellites, so it is operated by the CMA. So we have 2 constellations. That's one is the Leo, so that's a FY1 and FY3. FY3 is a 2nd generation series. And another one is the geostationary series. So that's FY2 and FY4. And also have a specific satellites also included in these atmospheres. So that's the atmospheric composition. So that's this. So this is the polar orbit. So now we have this, for the FY1, we have a series. And for this 2nd generation, from FY3A, now we launched 4 of the satellites. So this FY3D is just launched at the end of last year, and it's still under test. For the geostationary, so we have launched 8 satellites for the FY2 series, and this year we will launch the 9th one. That's the last one for this series. And then, in fact, we had launched the first one of the new generation. That's the FY4A in last year. So that's the overall. So this is statistics of the satellites. So in fact, for the development before the year of 2000, so our focus is on the development of the technologies. And for the first decade of the new century, the emphasis is for the transition from research development to the operational. And after the 2010s, so now our focus is on the data and the service quality improvement, and also the calibration validation for the data. So that's so this is the current missions: 9 in orbit, 5 in operation, 1 in trio operation, 1 in test, and also a joint program that's a townsite. So this is a payload for all these instruments for the FY1 series. So that's only from the 5-channel to the 10-channel via, and for the FY2, that's the geostationary. So that's a 3-channel to the 5-channel. And for the FY3 series, so we added a lot of new instruments for this series, so including, especially for the microwave sounders and imagers, and also for the ozone sounders. So this is the overall situation. And from the third one of the FY3, we added the GNSS occultation instruments. And for the new generation of the geostationary, we have 3 payloads. So I will go to some of the information. So that's the coverage of the Geo Satellites. So in fact, usually China has 2 satellites simultaneously to cover the all part of China. So this is the FY2E and FY2G, the coverage. And so for the FY2, the geostationary, so we have developed the scanning stringency from the normal scan of 1 hour to the regional rapid scan can to the speed up to the 6 minutes. So it's important for some of the extreme weather events. For the LEO satellites, so now it's the FY3B and FY3C is in operation, so it can provide global coverage 4 times per day. And the FY3D is still under test because it was just launched last December. So this is the capability of the FY3 series. So it has a global data acquiring latency within 2 hours for 80%. And the global data coverage with 2,800 kilometers swaths per day with the resolution of 250 meters. So that's now we have the receiving stations. So for the meteorological satellites, 5 inside China and 2 outside. And the FY series satellites had become important components of the WMO space program for the space-based observation systems. So it's important to maintain the reliable and standard observation in operation open data policy for the agencies. So for all the Chinese satellites, the data policy for these meteorological satellites is the most open one. Yeah, so it had data central open to public, so that's the satellites, and has more than 45 direct broadcasting users, mainly for the weather agencies, and also have more than 677 web-based international users. So this is for the latest programs. So one is the new generation geostationary satellites, the FY34A, launched in December of 2016. So the commission test in first phase for instruments with geolocation and calibration have been completed. This is last September. The commission test in second phase is ongoing. The second progress is that the fourth of the LEO, the polar orbit meteorological satellites, that's FY3D, launched in November of last year. So it is under the commissioning test, and it is expected to be completed within 6 months. That means maybe next month, so it can transit to the operational status. So this is FY3D is very important because there's partially failure for the FY3C. So this is important due to the power problem. The third one is the TANSAT. So this is a joint program. So it's, in fact, this is a technology demonstration mission. It's not an operation mission. So it's a joint mission initiated by the Ministry of Science and Technology and supported by the Chinese Academy of Sciences and also the Meteorological Administration. So the Ministry of Science and Technology, so the National Research Remote Sensing Center of China, it's an agency and most is the main funding agency. And the Chinese Academy of Sciences responsible for the development of a payload and also the satellite. And the National Satellite Meteorological Center is in charge of the data reception, processing, and distributions. So this is the situation. So it launched December of 2016. This is some information. The instrument, there are 4 instruments for this. So, this is the FY4. So I gave the wrong place. So this is the FY3D launch. Yeah. So it's the FY3D is an identical instrument with the FY3C. So we have both the optical, microwave, and the infrared, and also the valiant thunders for this satellite. So this is the first image of the microwave thunders, and then for the TANSAT, so there are 2 payloads for the TANSAT. So one is the CO2 spectrometer, another one is the cloud and aerosol polarized instrument. So this is the 2-1. So after about 8 months of the test, so the in-orbit commissioning was ended in the end of last August. And now the level 1 data can be assessed globally from the end of October of last year, so from the website of the CMA. So this is some comparison during the test period with OCO2 and also some measurement result. For the future, for the FY series, so now we launched this one, FY3D. So we still have 7 satellites. So within this decade, so that's a plan. The second series is for the ocean series. So it is operated by the ENSOS. So there are 2 constellations. One is the ocean color, so that's the HY1 series. And the second is the ocean dynamic environment constellations, so that's the HY2 series. And also include 2 specific satellites. One is the ocean environment monitoring and surveillance satellites, and another is the ocean salinity satellites. So that's overall of this program. So this is the HY series. For the HY, the ocean color constellations, so we launched 2, that's the first series. And now we are going to launch the second series. This is HY1A and 1B. So the 1A had ended, and the 1B is still in operation. And this year, we will launch the HY1C. And after this C and D, we will have a new generation for these ocean color satellites. And for the ocean dynamic constellation, there are 3 different satellites. So one is the HY2 series. So we have the polar orbit. Now we launched the H2A, and 2B will be launched this year, and also have the 2E as one of the polar orbit satellites. And we also have two inclined orbits together. That's next year we will launch HY2C, and then we will have a 2D. So to have a constellation, 3 satellite constellation together. So after this 2G, we will have the next generation. Another one is the wind and the wave series. The first satellite is the C4SAT, the China-France oceanographic satellite. And we will launch this satellite in this September. And the third one is the ocean salinity mission. So it is in the phase of the final approval for the implementation now. So we will have 2 payloads. One is the small slag, the interferometric, 2D interferometric. Another one is the L band plus several other frequencies for corrections. So that's the overall. And for the ocean monitoring and surveillance, we launched the Golfin. Golfin means high resolution in Chinese. So this first satellite is C-band SAR. And then we will have the HY3 series. So that's a continuation of the C-band frequency, C-band synthetic optical radars. And it is also considered that for the geostationary missions for the ocean applications, so one is the geostationary ocean color mission. Another one is the geostationary synthetic optical radar mission. So this is in the phase of the key technology preparations. So now we launched the 3, that's the HY1A and HY1B. So, and also in the year of 2011, we launched HY2A, and the Golfin 3 was launched in August of 2016. So that's overall. For the HY1A and 1B, there are 2 payloads. One is the ocean color and temperature scanner. Another one is the coastal zone imager. So there's only, the capability only limited to the near coast of China. So that's the limitation for these 2 satellites. So that's some specifications for this for these payloads. So for the ocean color and temperature scanners, it has a resolution of 1.1 kilometers. And for this coastal zone imager, it has the resolution of the 250 to the 2 kilometers. So that's the situation. And from the HY3C, so the HY series will have the capability for global coverage, not just simultaneous, but global capability. So that's a big difference. For the HY2A, it has 4 payloads. So one is the dual frequency radar altimeter, and the second is the scatterometer, that's a Q band, and also multiple frequency macro imager, and the tree frequency needle-looking macro radiometer for the vapor delay. So that's, and for the HY2C and 2D, that's the inclined orbit satellites. So the macro imager will be removed. So there are only 3 payloads for the inclined orbit satellites. So that's the plan. So this is the capability for one orbit of the HY2A. And for some of the assessment, this is for the assessment of the sea level products. So it is a joint work with CNES. So it has the similar performance with the Jensen 2 during the assessment, and also for the ocean surface wind. So this is a joint work with the EC WMF And also with the other agencies. Because for the HY2, in fact, we don't have the capability of near real-time data assess, so that's a problem. So for the C4 site, there are two payloads. One is the fringe payload. It's a wave scatterometer. So that's a scanning radar to obtain the wave spectrum. Another one is a scatterometer for wind vector, surface wind vector. So that's the SWIM. So this the French payload and the Chinese payload. So the following on, we will, for the ocean satellites, the HY2 radiometer will have the wide swath infrared radar altimeter and also a NIDA-looking synthetic optical radar altimeter to improve the precision. For the scatterometer, so our target is for high wind and our weather capabilities, so we'll have the KU and the C dual frequency polarized scatterometer for the follow-on. For radiometer, we'll have the full polarimetric macro imager, and for the C4 site, the future will be the wind and the wave missions, and we will add the Doppler capability for the ocean surface current measurements. So that's now we have the Pathfinder mission. That's the interferometric image radar with Tiangong 2. That's Chinese Skylab. So it was launched in September of 2016. So this is the two antennas of the instrument. So because due to the orbit, so we just have not so wide swaths. So this is some images with this. This is the inland water and also rain cells on the oceans and for the ocean waves. So that's the wave spectrum. So this will be flow with the future HY2 satellites. So the swath will be increased to 200 kilometers. So that's a challenging task. Yes. So this is the future for these ocean satellites. So I will not go to details. And the third one is sorry for this. This is the seismo electromagnetism satellites. Firstly, it was called as the earthquake satellite, but finally renamed as for the electromagnetic satellite mission. So it is the joint sponsored CNSA and the China Earthquake Administration. So it will be operated by the Earthquake Administration. So this is the measurement, including the electromagnetic field and waves, ionosphere plasma, and energetic particles. So that's payload. So for the first satellite, we have 8 payload together. So this is the configuration of this satellite. And in fact, during the implementation of the first satellite, the second one had been approved in 2015. So it is planned to be launched in 2020. For this second one, we added a new payload that's ionospheric photometer. So it's, in fact, it's a plus. So this is the data used for this satellite. So it has the principle of data, the opening data policy, so the data can be accessed. So the last one is just some brief introduction to the research program, the real research program. One is the technology demonstration missions, that's TANSITE, and also the Golfin series, the high-resolution satellite series. It was the CNSA missions, and also the Earth science missions. So we define this as the PI-led missions, focus on the Earth system science objectives. So we have 3 priorities. One is the water cycle, second is the energy cycle and balance, and the third is the biochemical cycle, and also the other missions. This is supported by the Chinese Academy of Sciences and the Strategic Priority Program on Space Science. So as the emphasis, we have 3 missions for the space weather. That's China and the ESA joint mission, and also solar mission, solar observation mission, and the coupling constellation mission. So this is a summary. So China has a comprehensive program, and meteorological and the weather is a focus. Yeah.
Okay, thank you very much for that. Very, very comprehensive overview of the CSA program. We do have time for a question or two, if anyone has one. I had a quick question. On HY2, I think HY2CD, you're planning to launch a swath INSAR altimeter.
That's for the follow-on. That's
for the follow-on?
Yes.
I guess that's primarily coastal oceanography, but that sounds quite similar to the ESA Cryosat mission, and so I wondered if you had a processing chain for those data over land at all, whether you would be collecting data over land and whether you would be processing it to, say, a level 2 product or something like that.
Okay, yes, because this mission is defined as application satellites, so we have a main user that's the Ocean Agency, and it also have, the data will also open to the research community, yeah.
Okay. Yeah, can you use the mic, Christine? Yeah.
Hello, thank you for this overview. You mentioned a new mission for ocean currents. Can you remind us? Because I didn't catch exactly what you said.
Oh, yes. So you know that now we measure the ocean current, surface current mainly with the synthetic optoradar, but that's narrow swaths and only one directly actually measured, one direction. So we use a scanning mechanism, that's a scanning scatterometer, to have the observation with 2 different directions, so we can have the current vector. Yeah.
Okay, thank you very much for that. So the last talk in this half of the session is going to be given by Josef Aschbacher. Yep, thanks. Who is Director of Earth Observation at ESA. And the title of his talk is Copernicus, Europe's Route to the Future. Oh, that sounds very exciting.
Thank you. Sounds very exciting indeed.
Bold, perhaps.
And bold. Okay, Europe's route to the future. I will not only talk about Copernicus, but also a bit giving a wider overview of what we're doing in Earth observation in general, so including the Earth Explorers, of course, the Copernicus missions, and also a bit the MET missions. Just trying to see how we proceed here.
The left button.
The left button.
Just click the left button and then, yep.
Well,
yeah,
okay.
That's it.
So before I do so, just a word on the Directorate itself. Some of you know it extremely well. Some of you may not know the Directorate of Earth Observation in ESA so well. So what we do is really a variety of measurements which we are taking from different satellites and missions. I was reminded when Mike was showing his parameters and his missions, there's a lot of similar measurements which we are taking. And of course, we are coordinating our activities. It's not that we are doing ours and replicate theirs or vice versa, but there's a lot of interaction and discussion ongoing on how we measure these various parameters. So what you see here is a long list of those, and this is really the majority of the Earth system parameters that are being measured by our satellites, which we are developing within the Directorate. So there's an extreme diversity and an extreme complementarity of these various measurements. This is the Directorate, what it is like. It is a similar size, slightly smaller than the Earth Science Division of NASA, if I compare the budgets. Think in terms of people, we are probably less than in the NASA Directorate, some 744 people distributed over different sites, most of them in Esrin, where the Directorate is located, but also a large group of people, the engineers in particular, in ESTEC, in Noordwijk. And then we have smaller sites in EXAT, which is in the UK, of course, in HQ, in Paris, and in Brussels, the Brussels office. So these people and this money is working on 3 lines of missions which we are establishing, Earth observation missions. We group them into science missions, Copernicus missions, and meteorology missions. Meteorology obviously being the first one since 1977, since Meteosat-1 was launched. ESA has developed all the meteorological satellites, either for itself when ESA was still doing meteorology itself, or now for EUMETSAT, which has been split out of ESA some 2.5 decades ago, and is now an intergovernmental organization on its own, but we work extremely close together with them. We build all their satellites, both geostationary, polar orbiting satellites. We develop them together with EUMETSAT. They define the user requirements, they define the mission requirements. We develop the satellites. The first one is funded by majority by ESA member states, but co-funded with EUMETSAT, and the recurrent satellites are funded by EUMETSAT, and at the launch pad we're handing over the satellites to EUMETSAT, then they become the owner, they operate them, and they disseminate the data. So this cooperation is working extremely well, and is really a good model of cooperation between different partners in Europe, and is actually often quoted as such that this is one where European institutions of different nature and kind are working extremely well together. I think the secret of the success of the EUMETSAT-ESA cooperation is that EUMETSAT has established its own channels of funding and channels of defining the user requirements, and they really have their met services in their boards, in their governance, which are defining what EUMETSAT should develop, and they fund those missions, and then with ESA we develop them from a technology point of view. The next line is Copernicus in the middle. It's also the largest Earth observation series of satellites today. We have 20 satellites being funded in the first round, some of them launched, some of them still under development. This is done with the European Union. The European Union, through the European Commission, is expressing requirements, which type of policy priorities, which type of parameters or policies are being addressed. We as ESA, we derive the requirements from these policy priorities. We define which satellites are necessary in order to satisfy those needs. We build the satellites, and we either operate those satellites through ESA or some of them through EUMETSAT, but on behalf of the European Commission. This program is co-funded. It is a rather large program going for 20 years now. It took a long time to establish it and get it on its feet and really make it what it is today. But I think it is fair to say that it is a very comprehensive Earth observation program which is existing and which is really measuring the various parameters on a very routine basis, long-term, with various instruments. I think the big characteristic or the message to give here, it is a fully operational program which has a visibility of decades or probably eternity in terms of measurements to be provided, similar as meteorology, but in Copernicus for other parameters like air pollution, oceanographic measurements, land measurements, and so on, but with a similar setup that we have long-term measurements provided through a series of satellites that complement each other. And then science missions, these are our core science missions driven by science requirements, defined by really top scientific questions through a committee. In fact, I've seen Christine in the audience before being a member of our new advisory committee for Earth observation, which is a committee of independent science experts. They're telling us what are the questions that need to be answered. Again, we have a call, we have a mechanism to look for ideas of good science missions, and then through a selection process we select one of them time after time, and we develop those as really science missions. Quite often, also the science missions are entering technology domains which have not been covered before. Sometimes it's happening that we are getting stuck halfway. That means that we are entering hurdles in terms of technology that are difficult to overcome, and this is something that, of course, is part of an R&D organization which has in its DNA to really to go into the unknown domain, and therefore sometimes face hurdles which are, of course, happening in this frontier of technology. So these are the Earthexplorer missions. You see the first 4 are the ones who either have been in orbit, like CoChair, or are still in orbit, and they are flying and taking measurements of various parameters. Then we have 4 other ones in the pipeline coming up and to be launched in the next, either this year or in the next years, which are done with our member states. You see one of them, EarthCare, is done with JAXA, a Japanese space agency, who is providing the core instrument, or one of the core instruments, the CPR, the Cloud Profiling Radar, which is being developed by Japan and delivered to ESA as a CFI. Some of these Earth Explorers are listed here. ILOS is the next one to be launched, and this is one of these missions I mentioned, which are causing us headaches sometimes because we are really entering a technology domain which has not been developed at all in the world anywhere, not even in NASA. Sometimes we look at NASA as our role model where we ask for advice if we are getting stuck, and we did so. And when asking NASA, they said, no, we have not engaged in this domain as well, but if you find out, please tell us because it's interesting, and we really would like to engage in this as well. It is the UV laser which is causing us this, or has caused us some of these blockages in terms of technology development, but once flying, this will be an extremely exciting mission because it does measure parameters not measured before, cloud-free wind measurements, 3 dimensions, with this instrument here. EarthCare is the next one in line, launched in around 21, as I mentioned, together with JAXA. Then we are building biomass, again, in cooperation with the US, which is measuring in P-band biomass globally, which is a parameter which is not so well known today and really needs better understanding and better measurements, to be launched in 2022. And then FLEX, fluorescence measurements, extremely important, extremely interesting mission, which will be combined with Sentinel-3, in fact, to provide measurements of the state of the plants and the health of plants at global level. So this is meteorology. I mentioned before EUMETSAT. Just very briefly, there are 2 lines, the polar orbiting and the geostationary lines. The current systems are METOP 2nd generation and METOP. Now we are working on the 3rd generation of Meteosat and the 2nd generation of METOP, which will be launched from the 20s or 21 onwards. One slide that shows the quality of or the use of satellites in numerical weather prediction. And this is quite an amazing picture because if you look at the yellow circle here, which is the measurement, the contributions to numerical weather prediction, accuracy or forecast accuracy, coming from satellites. The yellow one is METOP, the polar orbiting satellites I mentioned before, and they contribute, both of them, to about 44% of the forecasting accuracy to numerical weather prediction models. So in other words, they are more than an essential part of today's weather forecast. Without it, the weather forecast would be much less. The other colors are, you see the dark green color is the NOAA and Suomi NPP, similar contributions. Then you have the geostationary line, which is this light blue, interestingly, is not contributing as much as you might think. And the in situ measurements, measurements on ground of temperature, pressure, humidity, visibility, is the orange one, which is actually the same contribution more or less than one of the satellite contributions. So it's quite amazing to see how much satellites today are contributing to the accuracy of weather forecasts. So here comes Copernicus. These are the 20 Sentinels I mentioned before. We have numbered them. We should probably give them names, but they are numbered from 1 to 6. And then ABC in order to have the various elements of the series. The white dots are the ones that have been launched. The open circles are the ones to be launched. We have launched 6 satellites or 6 missions today. We are launching another one in a couple of weeks on the 25th of April. We're all getting very excited. It will be Sentinel-3B. You also see that on some of them we have major cooperations with partners. The Sentinel-5B mission is implemented and there's a strong contribution by the Netherlands, providing the Tropomi instrument as a major instrument to the satellite to measure atmospheric chemistry, and this has really been an extremely good cooperation of a national agency together with ESA, providing the inputs and the elements for the satellite. And Sentinel-6, mentioned by Mike already, a very strong cooperation with the US, both with NASA as the lead partner in the US and NOAA, and EUMETSAT in Europe as the contributors, co-founders of this mission. And I really would like to take this opportunity to thank NASA in particular and Mike for the strong partnership and the strong contribution over the years, which has been guaranteed through Sentinel-6 in particular, but also many other activities. Talking of Sentinels and Copernicus, what you see here is the curve of user registrations of Copernicus itself, and this is only one of the data portals where the registration is taking place, which is the central hub, data hub, which is managed by ESA, where other users are taking the data from us and then still replicating them from other sources. So what you see here that in the period of 3 years, we have built up 120,000 registered users at our Sentinel database. This is a quite steep increase compared to especially what we had before. If we add up all our science users we had in the Earth Explorers and ERS and ENVISAT, we had about 15,000 users built up. So now, over tens of years, over 2 or 3 decades, while here within 3 years we have 10 times as many users that are using our data. So we are really providing data now for users which we don't know anymore, which we have not met and not seen, and they are probably not in the room here. And this, I think, is good news because we are entering a domain where users on the website really are taking down this data and using them for whatever purpose they have good use for. In addition to these numbers here, there are major other users or replication centers that are downloading the data from us and then redisseminating or redistributing. One of them is NASA, another one is NOAA, another one is USGS in the US, also Geosciences Australia, which is another having a mirror site and is redisseminating. In Europe, we have several redissemination centers in member states who have agreements with ESA, and they can have mirror sites and they are replicating these data sources. And we have commercial companies like Google or Amazon who are providing access to this data. They are downloading all our data and then redisseminating them in very large volumes, and these numbers are much higher than what you see in this graph here because they have a very different access network. And I think this is good news because we are entering here from space a domain which goes really into all levels of society, into economy and all other aspects of society. Let me show a few slides on science and applications, and I'm not dwelling too much on this, just to highlight some of the examples we are working on because they are representing different domains. One example here is quite nice, where we have combined Sentinel-2 and Landsat data. We have taken this data over the period of a bit more than 1 year, but we have applied artificial intelligence and machine learning as the main elements to classify the various crops in this case in Germany over this period. The accuracy has been varying. On some areas it has been better than what you would normally get from classical ways of classifying the image. In some other areas it was not as good, but I think it was an interesting exercise to really use large volumes of data and applying machine learning on a more automated process in order to give, as a result, the land cover map as we see it here. So 15 crop types have been distinguished, about 2.2 terabytes of data have been processed, and this is now something that we have done together with Humboldt University in Germany. We will be further refining and working on. Another data set, extremely exciting, and we will have a major public event coming up in actually the day after the launch of Sentinel-3B, which was taken from Sentinel-5B. The satellite was launched on Friday the 13th of October last year. Very lucky day for us because the satellite performed extremely well, and the measurements which are shown here are first uncalibrated images just taken as they came down from the satellite, shown at a public event at DLR on the 1st of December. But immediately you can see that the accuracy, the spatial accuracy of these measurements is extremely good. You can identify pollution sources, cities or areas which are having higher pollution. In this case, it's NO2 concentrations. You see here the Po Valley extremely well, but also in northern parts of Germany and Netherlands, where some pollution sources are coming. And these images are provided every day, 3.5 per 7 kilometers, and we are working now at the calibration validation of it. And as I said, this data will go public in about 2 weeks from now. Another example, hurricanes, where we work with various partners. In this case, we have provided the satellite-derived information also to our partners in the US. And I think it's a good example where the use of these data has entered diplomacy, if I may call it this way, because the Department of State was, as you see here in this article, has issued a statement, an article where they describe the support provided by Europe to the US Department of State or to the US agencies in general, and thanking us in Europe for providing this support, especially during the times of Hurricane Irma and Hurricane Harvey, which have caused, as you know, major damages in different parts in Florida and in Texas. Another example, CO2 measurements. Of course, this is linked tightly with the Paris Agreement and the global climate debate. What you see here is concentrations of carbon dioxide globally. You see the variations, the annual variations in different seasons. You also see that the curve has reached a peak value of 412, which is, of course, a strong increase and the main cause of global warming. When I was at university, I still remember that the figures given to us at the around 1900, before the industrialization really started, was around 290. And now you see how fast this increase of carbon dioxide is going. It's about 9% at the moment over the last 15 years. Similarly, sea level heights. You see here measurements of from various satellites of sea level height. You see also the figure here that the trend is indicated today as being around 3 millimeters, 3.1 millimeters per year. You might think this is not a huge amount of increase. In 100 years, it would be 30 centimeters. But if you have read recently some of the publications, especially proceedings of the National Academy of Sciences, coming out in February, they said that this is not a linear trend, it's an exponential trend, and therefore the increase goes much higher, much faster, and will be around 1.3 meters by the end of the century. And if you have 1.3 meters by the end of the century, many countries will be in danger, many areas will be in danger, which will simply be flooded because the sea level is reaching their houses and their garages and their living quarters. Talking of which, Netherlands being one of them, but this is not showing an image of flooding, but of soil moisture, which is using our SMOS data. This was of June 2017, one of the driest months in the whole record of the Netherlands. You see the dry areas in red, and the wetter areas in blue in cubic meter soil moisture per cubic meter ground. The lower areas have a bit more, the higher areas have been drying out, and this is measured routinely by a company providing this service to a number of clients. Another example is Cryosat, it was mentioned before. Ice melting and ice coverages, here shifting grounding lines, which is the line where the ice will start to float. And these have been monitored and changed over time, and you see here the evolution of it. Let me say a few words in the last few minutes on some of the evolutions and some of the challenges which we are seeing. What you see here is some of these buzzwords which you are seeing and reading every day and which we are using. Most of them coming from the IT sector, and there the IT sector more and more enters our classical domains of space. Not only that the IT players are also becoming players in the space domain, but also, of course, in using the technologies which are being applied here. So this is something, of course, which we take not only note of, but we proactively embrace and see how we can deal with it. Another element which goes hand in hand is the big data revolution, so the number of terabytes or petabytes which are being produced by satellites. What you see here is only the ones operated by ESA, and you see a very steep increase. We are reaching 100 petabytes around 2026 of data which are being archived of our satellites, which you see here. Maybe quite interesting to see the dark blue lines are the ones from the Sentinels, which are today the largest producers of data volumes. Then you have the light blue lines, or the light blue bars are the Earth Explorers. The pink ones are heritage missions. These are missions that are not anymore in orbit, but we are providing access to this data, like ERS, Envisat, for example. And then we have third-party contributing missions. And I still remember when ERS-1 was launched in 1991, I was very eager to get hold of this data. I was trying to see how this data can be used. And some of the discussions in this kind of fora was, oh my God, what do we do with all this data? I mean, ERS-1 will produce enormous amounts of data, and nobody can handle them, and nobody can process them. But if you extrapolate 91, on the left side of this curve here, you don't even see it anymore. I mean, this is very small compared to the volumes we are dealing with today. And this comes, of course, with more and more satellites in orbit as well. What you see here is how many satellites are being launched, larger than 50 kilos, so not the small sats and the CubeSats are included, but larger than 50 kilos and not including metrology. And you see a very strong increase of the numbers of satellites getting into orbit. These are Earth observation satellites. The number 220 refers to a 10-year time period, while the number 562, as you see, is a 5-year time period. So this increase is really going extremely fast, which is a reality. Part of it is coming also from us ourselves, our Sentinel missions, but there are many other missions we have seen before. The plans of China, we have seen the plans of NASA, but also many others are contributing to a large array of these measurements. And some of these coming up on Copernicus are what we call the expansion missions, so Sentinel 7, 8, 9, 10, and so on. I'm not going into these, but these are candidates which we are evaluating at the moment. We are running phase AB1 studies for all of them, parallel phase AB1 studies, and some of these will at the end be selected to be further continued and missions to be produced. Obviously, CO2 is one of these candidates, but also questions related to the Arctic, which becomes more and more a political issue, but also a scientifically interesting domain where more knowledge is required. Agriculture, food security, vegetation, again, ground motion, these are parameters that are being measured by the next candidates of these missions. New space in Europe, we have seen before quite impressively what is done in America. Also in Europe, we have taken good note of what happens and stimulated or tried to stimulate a segment of new space players. There are some examples here. There are many more, of course, which are in the making and which are developing small sets. Maybe just 2 of them or 3 of them to highlight. Earth-I will be one, or has been launched recently, and will be one mission providing video images in color from space. Quite an interesting measurement to be taken. ICE-I from Finland has taken or is taking measurements in X-band, SAR mission on a small sat of 70 kilos. One would have never believed this 10 years ago, that you can fly a radar, synthetic aperture radar, on a 70-kilo spacecraft. But these are coming, they are reality, and we are working with them very closely, both in uptaking their data, in testing their data, but also helping them to improve some of their technology parameters to have the next generation in an improved version. Also, ESA is a market creator, so we are buying some of this data, very similar than NASA is doing, in order to test and see how this data can be used and integrated into major information chains, Copernicus, but also other domains where we are seeing how this data can complement some of the classical data which we are providing through Sentinels or Earth Explorers. And there we are working with various parameters, various partners which are working and providing these small sats. Maybe a last word, and I will wrap up very, very soon. This is the Phi Lab, which is our innovation lab, which we have introduced in ESA, in Frascati. It's actually a new building which I built last year, hosts about 27, 28 people. Only 5 of them are ESA staff, and all the others will be secondees or visitors from industry, from research institutions, from academia, which are working on a project, on an idea, spend 3 months, 6 months with us, and really explore new ideas and new domains that are not yet fully mainstream in our Earth observation domain. These are the domains covered. I'm not going into it for the sake of time. But just to say that we're also addressing other domains, high-altitude pseudo-satellites, small-sats obviously, but also mega constellations, which is something that is being addressed in this activity. One of the focuses I'm really pushing forward is artificial intelligence, and with it, of course, machine learning, deep learning, for not only the classification of images, but also ultimately onboard spacecraft in order to have intelligent acquisitions and therefore optimize the use of these resources. And as time is very short, I will be very quick now, but really I thought it is important to highlight the cooperation we have with NASA since many years, since 2010, where we have signed an agreement. These are the main domains where we are working: mission and technology, CalVal, field campaigns, Sentinel ground segment issues. And these are some of the achievements, and I'm not reading through the list, but it is a long list of where we have been working together. And of course, this will continue under the auspices of the new Decadal Survey. Thank you very much.
Thank you, Joseph. Oh no, stay there. So he was trying to escape without any questions, but I think we shouldn't permit that, and we do have time for questions for Joseph. Again, a lot of information to take in, a lot of ideas out there. Any questions? I mean, I had one. It's not directly, it's almost for all three of you. I mean, Mike talked about commercial sector, and I mean, I don't want to be pejorative about the whole of the commercial sector, but they don't always have the best reputation for looking after global commons, like the space sector, like space, which is a global commons. And you know, we've had the breakup of the Chinese space station that hit the news, and space junk is going to be an increasingly serious issue for all satellites in these low Earth orbits. And I mean, presumably a headache for all the space agencies, and something that, I don't know. Do you want to comment on that?
Well, there's not much to comment. I mean, just to say, yes, I fully agree with you. I think it's a major concern, and also we are very concerned of what that debris might interfere and interact with some of our other healthy spacecraft. It's an issue. Of course, in ESA, we have a policy that we are having a deorbiting policy, but I think many other organizations would adhere to this as well. But it's something that we have to watch very carefully. I can fully support what you say.
But I mean, companies like, is it Planet Labs? They have how many of these doves up? I don't know, 200 something?
290, I think, or 270.
So, the planet constellations tend to be rather small and in relatively low orbit. So they clean themselves up and relatively rapidly.
I mean, today, certainly today's, I mean, our standard Earth observation spacecraft fly around 800 kilometers. Yeah. These small sats, in many cases, around 400 to 500 kilometers, right. Sometimes even lower. Yeah. So it's a different orbit. Yeah. So today it's not an issue, yeah. But it might become an issue if they are using other orbits as well. Then I think, I would say the good thing is once they decline, of course, they burn up because they are so small and they basically disappear.
Right. Okay. All right. I think I'd like to thank all three speakers for a really fascinating afternoon. Thank you.
Welcome back to the second part of the Union Symposium, The Future of Earth and Planetary Observations from Space. And now we look from Earth away. But before we begin, my name is Stefanie Werner, and I'm the Planetary and Solar System Science Division President. Next to me, my co-convener is Özgür Karatekin, and our yellow T-shirt girl is Femke van Haster. But the main speaker, or the first speaker of the session will be Günther Hassinger on cosmic vision exploration of the universe.
Thank you very much. Thank you for the invitation, and I'm very happy to give this talk. I am the new director of science of ESA since only a few weeks, and I'm still in a very steep learning curve. And so please forgive me if I say a few wrong things. Actually, I have already learned a huge amount of things today, and I was really impressed and amazed how much information the Earth observation guys have on one object only. And now we turn around and we are looking at many different objects, and for each of these we are getting much, much less information. But in total, I think you will see that there are a lot of synergies between solar system science and Earth observations, and even going far beyond into the universe. So as a director of science, I'm actually in a tradition of a long series of directors, and we had just recently a very nice symposium to the 80th birthday of Roger Bonnet, who introduced the Horizon 2000 Plus programs, and all the 4 directors of science since him are there. And this should also show that there is a lot of continuity. I mean, we are standing on the shoulders of giants, and we are building on that in the future. I personally had the pleasure and also the honor to participate in the definition of the ESA Cosmic Vision program that has been put together maybe 10, 15 years ago. And ESA has the advantage in the science program that we can plan over very, very long time scales. The science missions are usually 25 years in preparation and so on. You have to develop new technologies. And so I now actually have the chance to see some of these missions fly and even develop new ideas. So what I would like to embark on by the end of this year is a new Cosmic Vision 2050 timescale, and I will come to that at the end of my talk. The ESA space science missions are very abundant as well. So what you see here are just the missions in orbit or completed, and then the pink bars are the missions that have been adopted and are prepared for implementation. But there is a whole series of missions that are selected or in the discussion for the future. And just for the benefit of this audience, the asterisks here are all the solar system missions. And so you see that there's roughly a balance in the ESA science program between astrophysics missions and solar system missions. And that is where the EGU is tying in very nicely. And so the ESA solar system missions, these are the big missions that are either in orbit or have already been completed to the solar system bodies. It's our fleet, which covers almost every part of the solar system from the sun, where we have SOHO flying, and then Solar Orbiter will fly soon, and then throughout all the inner bodies, the planets. Bepi Colombo will be launched by the end of this year, by October. And then very nice to just today be able to announce that ExoMars has just, the trace gas orbiter has just completed its aerobraking and is now basically ready for starting science operations as soon as the instruments are switched on and the software is uploaded and so on. So we are facing very new, exciting times, looking for traces of life in the Mars atmosphere. Then, as you know, the big planets, Jupiter, Saturn, have been very studied intensively, and also comet studies, the Rosetta landing and also the Rosetta orbit was really a masterpiece of European science. Now, for the future, there are a few elements missing on that chart. One of them is asteroids, where there are discussions about various different things, both safety aspects for near-Earth object asteroids, but also scientific and even maybe economic considerations about using asteroids to mine in the future. And then there's one very big gaping hole, and that is the outer planets. Now I need to go back. Can you go back? Yes. The outer planets, the ice giants, Uranus and Neptune, have so far only been visited once by the Voyager spacecraft. And so there's a lot of focus now for the next decade, maybe to go into the outer solar system, go back to the ice giants and study them then in great detail. On the other hand, the astrophysics missions are covering also a very broad range, the whole electromagnetic spectrum. ESA, together with NASA, a lot of these missions are done in cooperation with NASA or JAXA, is really covering the whole spectrum of the electromagnetic radiation. And I will only touch briefly on some of those aspects today. I would like to start out with some scientific highlights which are not necessarily coming from ESA missions alone, but just to give you a motivation why we do this thing. I mean, why is it still so dramatically important to do exploration and science? Because we are living in a golden area of discovery. The discoveries are raining down on us, and just last year we have discovered maybe 10, 15 things that we are mind-boggling and that we didn't know about before. And I just want to give you a few of these aspects, and they will also shape what our kids and everybody else would like to see further in the future. And what I would like to say is that the ESA Cosmic Vision program is already in a very good shape to address many of these questions, but it also shows us where we have to explore further. So one of these things is something that nobody has imagined. In October last year, we have discovered the first interstellar visitor. This is an object that clearly comes from another solar system, and it was zipping by the solar system, and it was discovered by a near-Earth asteroid watch program, PanSTARRS, in Hawaii. I had the pleasure to come from Hawaii, so this is part of my former institute's discovery. And what was amazing about this object is that it is actually looking, oh, so now it's broken out. Sorry. Let me get rid of that. Yeah, here it is. It is actually this elongated, very funny shape, which is causing it to create a light curve which is going up and down by a factor of 10 roughly. And when you look at the light curve down there, then you see from different telescopes, ground-based telescopes around the world, that there's a huge throw, and the only way to explain that is a very, very funny shape that nobody has really anticipated, and nobody really understands how to produce such a shape. And more measurements have been done, and just recently the Hubble Space Telescope actually has measured in greater detail and has found that this object may actually not be a cigar-like shape, but a kind of disc-like shape. Now, there are lots of speculation whether this is a real natural object or whether it's an alien spaceship. But if you assume that it is a natural object, then there should be about 25,000 such objects in our solar system at any time. And that means that we are expecting to see more of them. And this is a whole new class of objects which can learn us about maybe how the elements that are creating life have come down into the solar system and are raining down on us. So a huge new exciting field. Another exciting field is exoplanets. We now learn much more about the generation of our own solar system by looking at other solar systems. And one of these very exciting discoveries last year was this TRAPPIST-1 system, where 7 extrasolar planets have been found in a system which is not much bigger than the Jovian system with the moons. And Hubble Space Telescope measurements of 4 of these planets have shown that they very likely have rocky bodies, that they are rocky bodies, that they don't have bloated hydrogen atmospheres. And so they are in principle temperate, and they might be habitable. And so there are already artists that are drawing pictures of how such a planet might look like, and in particular how you could, from the surface of one of these planets, see all the other planets around, which are then bigger than the moon. But beware of that picture, because the star is actually a very small and very active star. And so these active stars can actually have a significant impact on the habitability of these planets. And so this is another field where X-ray information and planetary studies are important to learn more about how life has actually formed. And so there is, within ESA in the next few years, there is a bright future for exoplanet studies, because we have at least 4 missions where ESA has a significant impact. CHEOPS will be launched very soon. It's a small satellite project that studies the dips of exoplanets in great detail. There is the JWST, the NASA big next mission, which will also focus some time on exoplanets. There is Plato, and then recently we have selected Ariel. So these are basically a whole fleet of satellites that are measuring the wonders of exoplanets. And I come back to the exoplanet field because when I come to the solar system synergy, we learn a lot from exoplanets what we need to learn and to study within the solar system. Just another exciting discovery is our nearest neighbor star, Proxima b, has a planet, an Earth-like planet. And so far, none of our telescopes is able to actually resolve it. So we are now studying for the future what is necessary to really get images, pictures of these exoplanets. And then something which is a little bit far from the topic of this conference, but I think it's still very important because after all, when we study the Earth, we also study the elements of which the Earth is consisting. And now we have actually learned something which is completely mind-boggling again. We now know that the planet, the elements which we are made of are not only coming from stars, but there is also a very important neutron star component. This was the first time a gravitational wave event was discovered together with light. So this is like almost bringing the sound to the movies. You have the movies from astronomy, you get the sound from gravitational waves. And the two neutron stars that have merged have told us that actually most of the heavy elements, the gold that you have in your teeth and the iodine that you have in your blood, have actually gone through a neutron star merger. So we are not only stardust, we are also neutron stardust. And just by mentioning in passing, we are also part of the Big Bang because the water in our body is the hydrogen directly comes out of the Big Bang. I will skip over, this is my own hobby topic, black holes. But I would just like to mention that gravity waves, which have been basically also nailed down in the last few years, will have a huge impact for the future because the joint study of gravity waves together with emitting light, X-rays and so on, is a completely new field that has already told us a lot, and we are really expecting major new discoveries there. And this is two of the big flagship missions that ESA is currently preparing in astrophysics. LISA and Athena are basically in the center of the next decade, which we have to do right. And so that brings me to the strategy which we would like to put up for the next part of the cosmic vision definition. And this is also the strategy that we would like to follow in order to convince our ministers to give us a little bit more money in the next ministerial. And this is a kind of synergy between the astrophysics missions on one hand and also new possibilities in the solar system field. So what we would like to do is, for the next few years, we would like to offer new elements in the program which would enable this maximum synergy between LISA and Athena. That means really getting the gravitational wave universe together with astrophysics. But then a very exciting possibility that just came up in the last few weeks. I mean, when we visited NASA and we were discussing their strategies together with ours, it turned out that we might have a window of opportunity to actually do a joint mission to the ice giants. And that's something I would like to explain a little bit more in the next few slides. Then we would also like to start a small line of F missions, small missions, which can actually be used, they can use the Ariane 6 launch capacity, which cannot be fully filled with the science missions. And most of the science missions in the future are going to the L2 point, and there are no commercial passengers that can go to L2. So usually you can actually sell part of the access capability of the Ariane 5 for commercial flights, but for the science missions this is very difficult, and so we are actually planning to use the launch capacity to also create a small satellite line. And all of that is only possible if you are working very closely with the member states and if ESA can actually take over some more responsibility in the payload provision and in the systems engineering of the payload. So this is a package which we would like to offer to the ministerial meeting in order to increase the level of resources and enable these exciting new possibilities. So let me start with the ice giants. The exoplanet studies, in particular with the Kepler telescope, but also previously with European missions, have shown that most of the planets in the universe are actually in this band between the Earth and Neptune. So actually what we call super Earths or mini Neptunes. And it is not quite clear whether most of the planets in the universe are rocky or are gaseous. And the closest example, apart from the Earth, is actually Neptune. And the only thing that we know of Neptune so far is basically the flyby of Voyager in 1989 and the same with Uranus in 1986. So there's a very sketchy amount of information of our biggest, ice giant planets. And so this is a very strong motivation to go back to the ice giants and try to do something which we have done already with Jupiter and Saturn, to do detailed studies of the ice giants. And so science themes for the ice giant studies would be the interiors of these planets, what are they made of, the atmospheres, the magnetospheres, their moons. We might discover new moons and we can study the known moons very well, the rings, and then finally the origins, because the ice giants are in a realm where actually beyond the snow line of the original pre-solar nebula, and the question whether they have moved in and out of the snow line is also a very important one. And it turns out that it's almost like playing billiard in the next few years, actually, in the realm between 28 and 32. There is a constellation in the sky where basically you can fly to Mars, you can get gravity assist to Mars, then you can fly to Jupiter and get gravity assist at Jupiter, and then you can fly to Uranus and Neptune. And so you can actually reach both those ice giants with relatively large payloads and within a relatively moderate amount of time. And so that has brought NASA to the plan that they want to propose that as their highest priority for the planetary science in the next decade. And we would like to embark on this possibility and would actually like to explore European cooperation. Maybe ESA could take over one of those spacecrafts and fly to one of the planets, or we could add to the NASA spacecrafts by maybe adding a probe that goes into the atmosphere, or even a lander on one of the moons. So the possibilities are wide open. We just want to make use of the possibilities that the next Cosmic Vision program allows us. And then the next thing is, okay, this is the recommendations that came out of the NASA study in 2016. So the next step that we are planning to do with NASA is to kick off a joint study between NASA and ESA, where we would like to bring the European and the NASA scientists together to define better what such a mission could look like. Then it will be presented to the NASA Decadal Survey, and in parallel we will make a call within the European community after the next ministerial meeting, and hopefully be able to put this mission into the program. What we also have done, last year we have called the community and asked for new ideas, very broadly asking what are new ideas that are coming up, and it turned out that there were a relatively small number of ideas for the future, but one of them is in particular interesting, and that is to try to do something that we have seen in Earth observation, where these swarms of small sats are actually now getting more and more powerful. The planetary scientists have thought about what you could do if, instead of flying a big spaceship with many different instruments to one of the planets, if you would fly maybe a mothership and a swarm of small satellites. And so we have done a focused study with these, where we are studying what you can do with planetary science in small platforms. And that has actually been quite successful. There is a study going on where we have actually two different possibilities, either to fly to one of the rocky planets with a swarm of satellites, or to fly to a comet or to an asteroid. And we would like to, maybe just before I go there, there is a large number of bodies which would in principle be accessible to such a mission. So what is shown here is the delta V that you need in order to get there. And on the y-axis is the delta V that you would need in order to break and then basically go around that object. So the red points are rather hard to do basically orbit around because they have a relatively large delta V when they cross the object. But there's a group of objects which have a relatively low delta V, which would be available for a rendezvous and then maybe an orbit or even a landing possibility. So what we are trying to do is issuing an AO probably later this year and ask the scientific community to exploit possible targets, asteroids, comets, planets, which could make use of this F1 slot, which basically is a small system which could fly together with the next M4 mission. And so let me come to the basically long-term strategic planning. As you know, NASA is doing these decadal surveys every 10 years, and here I have zoomed out to a very, very large timescale going out to 2050. But the reason for that is that ESA in their large missions are already making determinations over a very large timescale. LISA and Athena are in the program. They have not yet been adopted, but they have been selected, and that means they will actually dominate the next decade. And we are already basically discussing what to do in the decades or in the steps after LISA and Athena. And simultaneously, NASA is doing their decadal survey every 10 years, both in the astrophysics and in the planetary sciences field. And so there is also the necessity to do to synchronize these two events. And so we have done that successfully, for instance, with the big NASA missions like Hubble, JWST, also the planetary missions to Jupiter and Saturn were all done in great cooperation. And so we have to already now set up the next set of kind of prioritizations where we are joining forces with NASA. And so my view is this is the current program basically with NASA, only with the astrophysics missions, but with ESA with the L missions and then the M missions. We have just recently selected the Ariel mission, as I showed you, and we are right now in the process to define what the next M5 mission will be. In parallel, there are the big, large ground-based telescopes that are also have to be folded in. So my view of the future is this whole slew. This is what I basically presented to you. On one hand, solidifying LISA and Athena and bringing them close together so that they can fly together as long as possible. And then I would like to interleave this ice giant mission if possible. So you see that this is M4, M5, and the ice giant mission would actually have to be launched even before the M5 mission. So it is something out of the line. It is actually, there is no M6 mission when you look at that, because the M6 mission has been canceled after the last ministerial because there was just not enough level of resources. So what I would like to do is to basically reinsert an M mission, but I have to pull it forward so that it can actually use this launch slot of 28 to 32. And that hopefully will be in conjunction with the big next NASA strategic mission. And then the idea is to have a continuation of the M missions, typically every 4 years have an M mission, but then typically every second M mission to fly that together with an F mission, which is the small approach mission. And then also we have to start discussing with the community and start to develop technologies and science cases for the next big L missions, which will basically follow the LISA and Athena. All of this can in principle be done within the level of resources plus something like a 20% increase over the next 10 years. This is a relatively moderate increase, and it is kind of compensating for a relatively large decrease in buying power, because over the last 10 years there was basically very little inflation correction and so on. So what I would like to do is build the science program to a level where it was when Roger Bonnet left it. And with this moderate increase, I would be able to really fulfill some of our dreams in this field. And I would like to stop here and be available for discussions. Thank you very much.
Hi, Alfred McEwen, University of Arizona. I'm the chair of NASA's Outer Planets Assessment Group, OPAG, and we strongly support an Ice Giants mission as NASA's next priority, so it's great to hear about your interest in that. However, there's a lot of competition, and this is not decided to be NASA's next strategic mission. We further favor Neptune over Uranus because of the large moon Triton, which has a good chance of being an ocean world with water in contact with the silicate core, much like Europa and Enceladus, and that might be essential to getting the community support to make that, in fact, the next mission. So does ESA have a preference of Uranus over Neptune, or is that an open question?
No, actually, the ESA interest in the ice giants is already reaching back 5 years or something like that. There was an ice giant mission that was actually proposed to the L2L3 selection, which then finally selected Athena and Lisa. But it was a very powerful mission. The problem that we had at that time is that we don't have the infrastructure, we don't have nuclear power, and we don't have the launcher. So it's clear that we have to do it together with NASA. What I would hope is that we could do a joint study between NASA and ESA scientists and then just define what those priorities are.
Great.
Jim Green is very excited about that possibility, and Thomas de Buchen as well, so I would hope that we can lift that to in
Great.
priority.
And you might invite a couple of astrobiologists to your study, because that's a big community. If you get their support, that can really help.
Okay, thank you.
Other questions? Then I have one.
Yes.
There's, of course, in the European Geoscience Union, is a lot of geochronologists and people who would like to have samples.
Yes.
So is there a chance for Mars or Moon sample return?
Yeah, so actually we are discussing with our Japanese colleagues to contribute to MMX, so that we would actually be able to also get access to Mars samples. And there is there's this funny divide between the science program and the human exploration program. So my colleague Dave Parker is negotiating and discussing with the NASA colleagues for a Mars sample return mission. And then there's a very exciting proposal for a small explorer on the US side to fly back to the comet Churyumov-Gerasimenko that Rosetta has visited, basically our comet. And it would really be wonderful if we could join that. They want to do a sample return mission from that comet. We already know the atmosphere very, very well from the comet. We know that it smells like a horse stable. And so we want to go and get some of that manure back.
Okay, then thanks a lot.
Thank you very much.
And the next talk will be ESAS, JAXA Small Body Exploration Program by Masaki Fujimoto.
Okay, yeah, the last conversation was a nice introduction to my talk, so thank you, Günther, for making that happen. So how does it work? Okay, yeah. So this year, 2018, is a very special year for us at Institute of Space and Astronautical Science of the Japanese Space Agency, because this year we will have the arrival of asteroid sample return mission, HABS-2, to its target asteroid Ryugu. And this mission is to return samples from this primordial asteroid in 2020, in 2 years from now, after doing the close proximity operation this year. And there will be a launch of BepiColombo to Mercury in October, and it's, of course, an ESA-led dual spacecraft mission to Mercury, and we are providing one spacecraft to do this mission. So then about Hayabusa 2. Well, this is, as the name shows, this is a successor to our previous mission, Hayabusa, which brought back sample from one of the asteroids. Now this time with Hayabusa 2, we are going to a very sexy asteroid that is supposed to be the source of key materials that enabled habitability of a planet. We think that, there's an idea that water and organic compounds must have originated from this type of asteroid, C-type asteroid. And we are getting there and getting the samples back so we can study how our habitable world is created in the early history of the solar system. So now the recent news is that we have a visual of the target asteroid. So what you're seeing here is a small dot, still a small dot, but still we know that our target asteroid is not a fake thing, and we are really getting there. And we will get there, we will arrive at the target in June this year, and the close proximity operation continues for 1.5 years. We leave the asteroid at the end of next year and coming back in 2020. That's the plan, and it's really starting now. And then, of course, we have the launch of BepiColombo to the planet Mercury. And yeah, because of its harsh environment, there haven't been many missions to Mercury. And following Messenger, which has left us very interesting question related to the planet and related to the space environment surrounding this planet, ESA and JAXA will be flying two spacecraft missions in October this year. October this year. So 2018 is a very special year for us, but it's also very special in the sense that it has been crazy 5 years of transformation happening at the Institute. And actually, both events, Hayabusa 2 and then the BepiColombo mission, two of them originate in a very different ways. They symbolically indicate the transformation that's happening, that we have been through. And then maybe that's the story. The new style of the Institute, the new way we run our missions is something I want to introduce to you today. And the key point here is that is this question: how to blend strategy from the agency point of view to the bottom-up process that the community loves. So it's this blending issue, it's a strategy issue, it's the international coordination issue that has been and still is the key issue of discussion and key story behind this transformation that's happening in these 5 years. So before talking about where we are now, I'd like to mention how we work at ISAS, the Space Institute of the Japanese Space Agency, JAXA. So the members at our institute consist of scientists, like planetary scientists or astrophysicists, and then space engineering researchers, and then engineers. And the star of our institute is indeed the space engineering researchers who have a cutting-edge ideas that they wish to fly. And it is the style of our institute, it is the style of ISAS to try to blend their wish into a mission. And it has to be this way because our institute is really small in terms of budget scale. So if we want to be visible, if we want to have our head above the horizon, you have to run our mission in this way. And it's this style of going, body go, makes planetary exploration mission to be the symbol of our institute. And that trend is getting stronger and stronger since the successful return of Hayabusa, bringing back the samples all the way from an asteroid, like this. And before talking about the transformation itself, let me tell you how our institute used to work. We used to have only a single launcher by the name M5, which launched Hayabusa, the first one, by the way. And since that was the only vehicle available for space science, our life as a space, mission-oriented space scientist seems to be rather simple. And it was a straightforward path story to plan a mission. You just come up with a nice idea that you can fly with this launcher. And that's all it mattered. And that's why this M5 launcher is not that super capable, so working together with the space engineering researcher has been, and still is, the key in making a very nice mission within the resources limited to us. So that what ISIS used to be like until 10 years ago or something. And things that's happening for 10 years, but we haven't really been determined to face the new way of making space missions. But I think now we're determined now. We've been working to determine ourselves for 5 years, and now I think I can tell you what the new shape of this institute is like. And one thing I really want to emphasize here is that the style of strong interaction between engineering and space science remains the same. Because as I said before, it has to be this way because we are resource limited, and it has to be, we really have to go to the edge to come up with a nice mission so that we can be, above the horizon in the global landscape. So the spirit stays the same, but there are new features. And new features has two keywords. It's the injection of strategy from the institute point of view, from the space agency point of view. And the other keyword is the enhanced function of the institute, as of the agency for international coordinations. And I believe that both of these two items enable smoother international collaboration in the future. So now, reformed space science program of ISIS JAXA. Here's what it is like. Now we have 3 mission categories. The first one is our L-class mission to be launched by our H2A or H3 launcher, the biggest launcher available in Japan. And the cadence of this L-class mission is like 3 missions in a decade. And we also have smaller missions. We call it M-class mission, and that is to be launched by our solid motor by the name Epsilon, which is a much smaller launcher. But again, because it's smaller, it's a smaller mission launched by a smaller launcher. The cadence is every other year. So every 2 years we have an opportunity, and that should be something you might want to think about in terms of international collaboration. And of course, beside these 2 missions to be led by JAXA, we have set up a category in which we hope to provide Japanese colleagues an opportunity to be a part of the missions led by foreign agencies, especially those grand missions that we at JAXA cannot afford, like JUICE mission or CESAR mission, which I'll be touching on later in my talk. And when it comes to these kind of mission, I think, well, in the past we just left it to the scientists' effort. They should talk to their friends, and they should come up with an idea, and they should coordinate everything by themselves. And I don't think that's not an efficient way of doing the business. Now, what we are thinking of is that we should intervene, we should step into the process, and we should guide the scientists so that there can be a mutually fruitful way of collaborating with Japanese scientists being a part of the foreign missions. So that's where we are now. These are the directions we want to move into the future, and then we think we have 3 engines to drive our move. So unlike what it used to be, we used to have only a single launcher, so we didn't have any idea like a program or something. But now that we have multiple ways of making our mission happen, that kind of motivated us. Well, that forced us to think about something like a roadmap, something like a program, something like an idea for a program that you can share with your colleagues, so that you can have some reasonable expectation into the future. And for the small body exploration, I think we do have a very nice roadmap, which I would like to introduce to you here. And this is what the program looks like in a graphic presentation. So if you look at this, you can realize that our small body missions really concentrate on those small bodies born outside the snow line. And why do we care? Why do we have to, why we concentrate on those small bodies in the outer part of the solar system? We are constantly, we think those small bodies matters because they are, tightly linked to the very important question of the habitability. Because, if you just think about it, if you just realize that Earth must have gone super dry without no water in its body, water, which is a key ingredient to enable habitability of our planet, must have come from outer part of the solar system. And we think that it's the small bodies migrating from the outer part of the solar system, from the outside the snow line, that delivered those key materials like water or organic compound to enable the habitability of our planet. So understanding that migration process is important, but at the same time, there are many categories of small bodies in that outer part of the solar system, and we don't know why do we have those, multiple categories. Most of them, all of them must have born like comet, with a simple mixture of ice and rocks, but eventually they evolve into something like a primordial asteroid or active asteroid. So what's happening there, and which category of small bodies were really effective in bringing the habitability enabling materials to our planet? I think that's really a good question to ask. So our plan is to go to the small bodies born outside the snow line and understanding how they have evolved in time, and try to understand the migration process, try to understand the transport process of water and organic compound. That's the background philosophy of our small body exploration program. And when it comes to the program elements, for those to be launched, for those to be categorized as our L-class mission, we do have Hayabusa 2, which has been launched already and is getting to its target now, as I said at the beginning of my talk. And this mission is our second asteroid sample return mission, and having NASA OSIRIS-REx as its brother. And it's going to be a sample return from C-type asteroids. So it's like, through the analysis of those return samples, we can study about the potential source body of water or organic compound that enable the habitability of our planet. And we are also having a very nice collaboration with our European colleagues. So this is, this shows how we sample from the surface of an asteroid. But before doing this complicated operation, we want to understand the nature of the small body itself. And for that kind of reconnaissance science purpose, we call it multi-scale science, by the way. It's like, it's like global observations and global observation from the orbiter, and then the nanoscale observation by looking into the samples. But if you are landing on the surface, and if you have a microscope, like our mascot lander do, which has been provided by DLR and CNES, you can have a microscopic point of view that's sitting in the middle between the global view and then the nanoscale view. So having mascot really enabled us to do the multi-scale science of those materials we're getting from this asteroid. And this small, nice, charming addition to the main mission has been really enhancing the science that we will obtain from this mission. So international collaboration really matters. And then another mission in this, another L-class mission in this small body roadmap is the Martian Moons Exploration, MMX. The mission is to be launched in 2024, and it will go to Phobos and Deimos, 2 moons of Mars, and then return samples from Phobos. If we return samples from Phobos, the obvious question we'll be answering is to reveal its origin. We don't know how Phobos is made, and there are many interesting discussions about this, small rock just orbiting around Mars. But still, revealing its origin is an interesting question. But what is really more important is that when we believe, once we reveal its origin, we should have a deeper insight into the behavior of the small bodies in this area of the solar system. Mars is sitting at the kind of a boundary between the inner part of the solar system and the outer part of the solar system. And understanding the behavior of the small bodies in this part of the solar system matters a lot because you can think about the strong linkage to the transport process from outside the snow line to the inner part of the snow line. So because the currently available idea for the origin of Phobos tells that there must be small bodies playing a key role in its forming, in its making. So I think it's not only revealing the origin of Phobos, but we can get a deeper insight into the transport process from outside the snow line. And that's why we think this is a nice L-class mission. So I've mentioned 2 sample return missions from small bodies, but not all the small bodies, it's not easy to, some small bodies are very charming, but yet not easy to do sample return missions. And for those missions, we try to fly a small mission to make a flyby observations. And this is an example, Destiny Plus. It will make a flyby observation of an asteroid by the name 3200 Phaethon, which is supposed to be the parent body of Geminid meteor shower. And this is like active asteroid, which is releasing dust particle into the interplanetary space. And what is an active asteroid? It's something it's something like sitting in the middle between comet and asteroid, but still that's a nice question to ask. So we wish to have some more data trying to understand its origin. But this target, Phaethon, is not easy to do sample return. So our choice is to fly a small mission that will make flyby observations like this. And in addition to this flyby observation of Phaethon itself, we will make a cruise dust analysis during its trip to the asteroid. So this mission is like a dust science driven mission. We do care about dust particles in the solar system because dust particle is one of the most likely vessel to make transport of materials to happen within the solar system. So again, this mission is a small mission. It's going to be a flyby mission, but still has strong linkage to the background theory of our small road-up exploration. And there are, there are many interesting bodies that we just cannot fly our mission to. There are small bodies that's very attractive, but that requires big missions, bigger than what JAXA can afford. A typical example is the icy moons of Jupiter. So we try to be on board. We try to get there on board ESA-led JUICE mission. And of course, when you talk about sample return mission, maybe one of the ultimate sample return mission you can think of is to get samples back from comet, to get samples back from comet. And CESAR is one of the finalists of NASA New Frontiers 4 framework. And JAXA provision of sample return capsule for this comet sample return is currently under step 2 study. So this is an interesting framework. As I said, at ISIS, the interaction between scientists and space engineering researchers is a key word. And in this framework, it's a space engineering researchers' effort that became visible, and our US colleagues asked us to provide this key element in the mission. And when this happens, it's like a gift from our space engineering researchers to planetary scientists, because this framework will enable our planetary science to enjoy analyzing the samples brought back from the comet. So again, this really symbolically shows how we work at ISIS. So we have multiple mission lines like L-class mission, M-class mission, which means that it's nice to have a roadmap like this, which I just explained to you for the small body exploration. But this doesn't have to be just only for the small body exploration, but strategic planning for the whole ISIS space science program is kind of wanted. And but this kind of roadmap means something only when it's backed by a strategy. And then the question is, who, with the input from the community, will be the coordinator for the strategy? And another thing is that there is an even more stronger need for the international collaboration, because in both L and M class missions, for L class missions, it has to be a very good mission, because this is our largest mission. For M class mission, it's a very resource limited mission, which means that it really requires a good idea that fits within the severe constraint to make it a good mission. And if you want to have a good idea, you better talk to more people so that maybe you can catch good ideas. So both have different but the same reason, but different but good reason to go international, for nice instrument to be available from abroad, or for broader discussion to shape up the mission idea. And then in this broad framework of international discussion, who should be the coordinator for the international communications? So these two items, the strategy, the need for the coordinator for the strategy, the need for the coordinator for the international collaboration, points to the fact that maybe the space agency, the Science Institute of the Space Agency should step in to the mission building process from an earlier phase than we used to before. And that's really happening already in the sense, and I'd like to tell you some okay cases that's going on that just happened recently. For the case of MMX, the Phobos sample return mission, among the 3 instruments of the highest priority, one will be from the US and another will be from France. And we at IDA thought is the best approach. And we have performed a dedicated AO for these 2 opportunities. And the conversation between NASA and CNES started very early, and that really, at least compared to the practice in the past. And so this early conversation and this early determination really made the smooth international collaboration happening for this mission. In the case of Destiny Plus, as I told you before, there are 2 key observations for this mission. One is the flyby observation of Phaethon, and the other is the dust analysis during the cruise. For this in-situ dust composition analysis, it's only a group in Germany who can provide such an instrument. So we need to talk to those people, the Stuttgart University people, and this coordination of getting the instrument from Germany was completed at the very last leg of the pre-phase A, just before the mission become the pre-project. So it certainly was smoother if the conversation started earlier, and that's a lesson we learned from this case. But still, we did better than what we used to do, and then that really enabled this new effort to really enable this Destiny Plus mission to be more attractive than it could have been if we just followed our previous practice. So as I said, it's happening already in this branch of space science, and why not in other areas, in the whole branch of space science. I hope it will happen into the future from now on. So this is my last slide. JAXA allocates high priorities on international partnership in order to maximize the science return. And JAXA continues to promote international collaboration in missions of various scales, L-class and M-class, and of course, our participation to foreign missions as well, for an efficient utilization of limited resources. And I think for this to happen in a smooth way, building and sharing roadmaps will be the key, enabling early phase conversation. And I think early phase conversation is crucial in implementing the international collaboration in a smooth way. And it's our hope, I think we are moving in that direction now. Thank you very much.
Questions?
I'm Håkan Sweden from ESA Tech. I know that JAXA and ISA in the past have done several tests with solar sails. I'm not so sure about the results on that. Was that successful? Is that something that you might use in the future?
Yes, there is one mission which I skipped. One of the mission ideas for the L-class mission is this one, solar power cell mission. it has a solar power cell which is whose size is like 40 meter times 40 meter. And the idea is to fly to Jupiter Trojan and make an in-situ, and then deploy a lander, and then make an in-situ observation on the surface. So it's there. It's very challenging mission, and it's in competition with another challenging mission from cosmology. So if you're on the planetary side, you should support this mission, but if you're from astrophysics, you should support the other mission. So that's where we are now. And we will select the mission for this slot at the end of this year. So you will know by the end of this year whether we will fly another super challenging mission to the small body or not.
Okay, thank you.
For a general scientist who would like to participate in any of this mission and is not part of an instrument, is there any strategy to involve them?
Yeah, you should beg your science director. With JAXA, DISA has a nice collaboration, so whenever you raise the issue, maybe we'll think about this. But again, yeah, well, in general, I think we're starting to abandon the old thinking, you know. Once you fly a mission, the data you gain is much more than you can analyze by yourself. You know, Japan is a small community, and we don't want to be ignored. We don't want to be looked down upon. But you know, as long as we stay on the horizon, I think we're happy to collaborate. And then it doesn't have to be our result. You know, we are happy as long as we can contribute to what's going on the global landscape. I think we're starting to change our mindset now. Before we can fly only small missions, we used to think that we're nothing. We're small fish compared to ESA and NASA. That used to be we used to have that kind of losers thinking. But nowadays we think we're getting a little bit visible, more visible than we used to, and that kind of relaxing the people's mindset. And I think this relaxed attitude makes people more open to international collaboration. Maybe I'm optimistic, but that's my observation. Yeah, and I'll push into that direction for sure. Yes.
Thank you, and thanks for the presentation. The next talk will be NASA's Heliophysics Research and Space Weather Services for the agency's robotic missions by Alex Young.
Okay. All right, thank you. Especially thanks for everyone for staying for the last talk of the day. So I'm excited to be here. This is my...
You don't want to...
No, I'm good with this. Yeah, hopefully I won't start moving around too much. So I'm excited to be here. This is my first time to an EGU meeting, and it's also great to see the work of colleagues in Europe and JAXA. I've got my start on missions in astrophysics and solar physics like SOHO and Hino Day. So what I want to talk about today is a little bit about heliophysics as a science, but how that's led us into the need within the agency, and I know this need is for all of the space missions across the globe, to support our spacecraft in dealing with the harsh environment that we have to deal with in terms of space weather and the heliosphere itself. So to start off, now heliophysics is a younger science. It's actually come out of solar system science as well as astrophysics and earth science. And it was something that was combined together specifically at NASA to form a fourth science part of the Science Directorate, in addition to earth science, solar system exploration, and astrophysics. And in this case, it's a science that is, in fact, a system science, much like earth science, as opposed to astrophysics or planetary science. But the realm is much larger. So it's the realm of the sun, the influence of the sun, and the extent of this giant plasma bubble that it creates around the solar system we call the heliosphere, its realm of influence. And how what comes off the sun interacts with everything in the solar system, the planets, including our own, of course, as well as all the smaller bodies within the solar system, but also, and what I'll focus on today, the instrumentation and the spacecraft that we put into the solar system. And that's a huge issue that was not as obvious to us, even though when we first put spacecraft out in space, the first thing that we encountered were the Van Allen radiation belts. Realizing quite quickly that it is really nasty out there. And it's very difficult and challenging not only to launch a spacecraft and put it in orbit somewhere, but also to maintain it and keep it surviving in this incredibly harsh environment. So fundamentally, the first goal of heliophysics at NASA is to understand the fundamental science. The fundamental science of plasmas and electromagnetic fields and how they interact with each other and various bodies in the solar system. And next, it's going out to that more system science, connecting all the pieces together. And in particular, a large focus, of course, is how that impacts us and the environment and our interface from space to the upper atmosphere into the atmosphere that we live in. And then lastly, this gets into the hazards and the survival of both human travelers in space as well as robotic missions. And I'll talk a little bit about human space flight because some of what we've learned from that and the operational aspects of it carry over into robotic missions. So in terms of the broader science in heliophysics, just as in the other disciplines, we focus very much on newer technology, trying to use small sats and CubeSats. Low-cost access to space is very important with things like sounding rockets, flying through the aurora, flying through the atmosphere, as well as new ways to create micro-instrumentation to do in situ measurements. And then, of course, data. And as we've seen, especially from the presentations from NASA and ESA, the data volumes are monumental and they're increasing exponentially, requiring more sophisticated ways to serve the data, to access the data. Traditional database methods are becoming more and more cumbersome, as well as looking at things like deep learning, artificial intelligence. And so we focus on both a broader space science data archives and access points, as well as ones for specific missions. And then, of course, there's modeling, which is in itself its own kind of data. You know, modeling is becoming more and more sophisticated, especially the models that are used in Earth science, but also the ones used in heliophysics and the models in heliophysics which apply to other planets, things like modeling magnetospheres of other planets besides our own, become incredibly complicated as we try to understand with real physics-based models. We're creating our own additional data sources. So we look at different types of models, but we also have created something in cooperation with other national agencies as well as across the globe, the Community Coordinated Modeling Center. And originally this was, again, something that was designed with heliophysics in mind, but it's quickly expanded. We're including models for the flyby of Horizon. This was a challenge to try to bring the most out of the data when Horizons flew by Pluto, to understand the plasma and space weather environment as the spacecraft reached there. But this is even going farther into things like exoplanets, understanding the habitability. As was mentioned, the TRAPPIST is a really exciting system, but that star is extremely active. And so understanding those type of environments and being able to model that, model the heliophysics for exo systems is critical for our science. And so the Community Coordinated Modeling Center is a place where scientists can both host their models as well as access models and run them at their own request. And so this has set up a really powerful collaboration. But what's come out of this is the need to use these models for space weather. So what happened in the NASA context was basically NASA missions contacting the members of Heliophysics, the Community Coordinated Modeling Center, saying, look, we're seeing these anomalies on our spacecraft. Can you tell me, is this something that has to do with my instrumentation? Is it something that is simply a fluke, or is it got something to do with space weather? You know, was my spacecraft hit by a particle? Did I experience a single event upset, surface charging, or something of this nature? And the requests coming in from spacecraft operators within the agency developed the need for the agency to start its own space weather forecasting system. Because the way things are set up in the US currently, NOAA is the official agency for forecasting space weather events directed at Earth. But NOAA doesn't care about what goes on outside of the Earth, but it's also not thinking in terms of the NASA and NASA's partner assets that are in space. And so that has led to the development of a space weather service for our agency and for the partner missions and instrumentation that we have. And then one of the things that's also come out of that, in terms of the importance of communicating and educating about our science, was the development of boot camps within the group at Goddard, at NASA's Goddard Space Flight Center, to bring in not only students in heliophysics, astrophysics, planetary science, earth science to learn about space weather, but also to bring in spacecraft operators to do training, to do extensive training on how to understand the data that's coming in, how to interpret it, and how to make use of it, to both educate them, but also allow them to have a better back and forth communication with the space weather services that NASA is providing. So in that case, we have several different boot camps through the summer, and it's also become almost like a graduate student summer school, and even space science teachers are coming in to learn more about space weather. And all of this is centered around the heliophysics observatory fleet, okay? The Great Heliophysics Observatory. It's a set of missions that are NASA, NASA ESA, NASA JAXA. So they are NASA-driven as well as partnership missions that provide information about what's happening at the sun, all the way out to the edge of the heliosphere with the Voyager spacecraft. And in fact, ESA will soon be launching the Solar Orbiter mission, which NASA is a partnership in, which will bring us extremely close to the sun to show us this environment in a new way. And ultimately, we'll also be having the Parker Solar Probe, which will be flying into the sun's corona, basically the place where all the action is, where everything is going on that's accelerating the solar wind, that we think is driving the million-degree corona, as well as what is creating the phenomena we call space weather. And so I'm going to take a little bit of a side, and I'll talk about in a second what space weather is, what do I mean by that. But really the issue then is we have this fleet. We realize that we're looking at the sun, and we're also being impacted by the sun. So we have spacecraft which are monitoring what's happening on the sun, and in fact, we have spacecraft that are being damaged by what's happening on the sun. And so not only do we have those, but we have the Earth-observing fleet, we have the planetary fleet, not only what's in space, but what's on the planet. What's happening on Mars is impacted with a no global magnetic field, but more importantly, with an extremely thin atmosphere space weather, in particular charged particles, can have a huge impact on instrumentation. And then lastly, astrophysics. So all of these spacecraft are under the influence of what's happening on the sun and what's happening through the solar system. So these are just some of the missions that we've had direct support for, everything from geocentric missions near Earth, heliospheric, sounding rockets, as well as some international collaborations. There are constantly new missions that are finding various anomalies. And so this way, it didn't start off as a coordinated effort. It was basically just an operator calling up and saying, please help me. I don't know what's going on. My spacecraft is acting really wonky, and I'm not really sure. Can you give me some idea of what might have happened? So what's happening on the sun? So we have magnetic energy, which is released on the sun in an explosive way. And the first thing that we get is a huge flash of light through the entire electromagnetic spectrum, what we call a solar flare. And that reaches the Earth right around 8 minutes, the light time to reach Earth. And that phenomena can last minutes to hours in terms of both the length of it and the impact on the planet. We also have something called a coronal mass ejection. Billions of tons of solar material and magnetic field are blown away from the sun, millions of kilometers an hour. So they actually reach the Earth in the fastest case, somewhere around 15 hours. That would be an extremely fast event, usually somewhere on the order of 2 to 3 days, okay? But both the flare, the explosion on the sun, as well as all that material as it's plowing through the solar system, can accelerate charged particles to ultra-relativistic speeds. So we have one more part of this, which is a particle storm. These are protons and electrons and some larger and some ions that are traveling near the speed of light. They contain a huge amount of energy. And they actually can get to Earth, or even to some place like L1 where we have a spacecraft as early as 15 minutes, and they can last for days. Okay. So each one of these phenomena has a separate impact on spacecraft as well as humans at Earth. Now I'm focusing on what's happening at Earth, but many of the phenomena here apply to both other planets as well as spacecraft freely flying through the solar system. So what we get are several different things. If we look at the solar flare, you have a loss of signal for high-frequency communications, HF communication, but you also have a loss of lock on the global navigation satellite system, GPS. These charged particles can also cause a loss of signal near the poles, where the particles can more easily stream into the upper atmosphere, or the magnetic field's at its weakest. We can also have, as I mentioned, single event upsets, as well as particle dosage for both technology as well as humans outside of the protection of the atmosphere. And then we can have more microelectronic upsets, and this is even an issue for passengers in polar flights. More importantly, for workers on an airplane, they're technically actually considered radiation workers. And then with the geomagnetic storm, we have charging of the spacecraft from electrons. We can have transformer and voltage overloads on the ground, on the power grid, that can take out power grids on a country or even continental scale. Again, loss of lock for signal, and then more high-frequency interactions. So these are the different types of interactions that those three phenomena can create, and this shows you the the rough time scale, both of the phenomena reaching us as well as how long we can see the impact of what they're doing. So, and what I want to show you is from the operational point of view. Now I'm going to show you an example for human space flight, but this is actually something that applies for how one thinks in terms of operations with a spacecraft or with something like the International Space Station, of how you deal with some type of space weather event. In this case, a particle storm, that blast of ultra-relativistic particles that comes from the solar flare eruption as well as the CME driving shocks through the solar system. So you have the solar energetic particles. They're generally interested in ones that are above tens or hundreds of mega electron volts. And let's see if this will. It's not moving forward. Can you progress it for me? Okay. So you start off, I'll just tell you each one to progress, please. So you start off with basically you provide all clear to, in this case, astronauts on the ISS. Next one, please. Then we have something that's indicating the possibility of an eruption. In this case, it would be an extremely large sunspot. And if that sunspot were at the right location on the surface of the sun, it would mean that it's magnetically connected to a location, in this case, the Earth, okay? Because those charged particles are going to follow a magnetic field line that bends away from the sun. In fact, it's going to come like this. Next one, please. So then you have the flare onset. And in this case, instead of, let's say, powering down a camera on a spacecraft that's going to be sensitive to high energy particles, this is the case where someone in space would move to a protective area on the spacecraft. Next one, please. Everyone would enter the storm shelter. Go ahead. And so they would keep the crew, or in this case, the spacecraft operator, aware of the status of this event, looking for where it's decreasing. When you reach the end, then basically the time to leave the shelter is over, or for a spacecraft, the time to turn a particularly sensitive camera back on. Okay. Okay. So keep going. So one back, please. Yeah. So you want to know what are the observations and models that you need to support this, and what are the hardware architecture requirements to support the observations. So this is the back and forth between the space weather services and the spacecraft operators, and in this case, the human spaceflight system, on how to protect the assets, both of human and robotic assets. Okay, let's see if it'll. So from the national perspective, and this has actually led to international agreements, nationally there's been the development of policy for space weather, and this is something that's come about relatively recently. There was a national space weather strategy that came out of the National Science and Technology Council in October through the Obama administration. They then created an action plan, and this is an interagency, includes not only NASA and of course NOAA, but emergency organizations like the Federal Emergency Management, or FEMA, Homeland Security, even DOD and the military, because all of them have stakes in what can happen with a space weather event. This led, again, to some executive orders. And finally, the crucial part is it's leading to legislation, because ultimately, until it gets to legislative bodies, nothing's really going to happen. So that's where this has led. And then, of course, these strategies are also being worked with partners on an international basis. Okay, so there are international organizations headed by members of ESA, NASA, and other organizations around the globe. And so lastly, now this actually might be, depending on the direction of the current administration, this might actually be not the direction, but I think this is a nice overview of looking at the bigger picture of how we think about science, exploration, and technology, both on human spaceflight level, as well as moving out into the deep solar system and thinking about ultimately putting more and more assets onto planetary bodies, and how we bring all of this together to develop a space weather plan and a heliophysics plan to support assets. So space weather has really only come into the forefront over the last 20 years, and in particular, since SOHO, that's really what brought space weather to the forefront. But it's here to stay, and certainly it's something that requires, you know, at the US level, an interagency, but this is really an international issue, and it's something that is moving forward. There's been a great deal of momentum picking up. But this is an important aspect of all spaceflight, both robotic and human spaceflight, of understanding this incredibly harsh and complicated environment and how we and the things that we bring out into the solar system interact with that. And ultimately, on a side, understanding this, again, from the science point of view, and maybe in the distant future from the vast exploration point of view, bringing in this to extrasolar planets is also crucial, because understanding those environments really lead to us better understanding both the formation of life and the evolution of life, not just in our solar system, but in other solar systems. So, thank you very much.
Questions?
Very nice talk, thank you. I was always interested about the radiation issues on the flight to Mars. I mean, what's the current thinking? Is that, would a solar storm be survivable?
Well, the biggest issue really, even though solar storms are certainly important, the biggest issue is actually still cosmic rays. And that's really, not to downplay what's going to happen there, but really cosmic rays are, I think, the bigger issue. And so that's something I think has to be the biggest focus. But having said that, I think the biggest things that we think about are speed and how fast we can get there and ways to mitigate it. Because there's a lot of very clever ideas on how to deal with this in terms of technology and shielding. But most of them are not very practical at this point.
Actually, following on this point, we have performed in the International Academy of Astronautics a study actually of radiation hazards on the way to Mars, also secondary radiation coming out of the surface of Mars, and how you, so clearly there is we are not able at the moment to
Yes.
safely travel to Mars. So maybe we should go to the surface of the moon and use the moon regolith as a shield and the water.
Yeah.
But actually on this line, I was wondering, how do you collaborate with the human exploration system? So do they have a way, for instance, to put experiment like they did in the past, experiment to measure radiation and some environment factors on deep space missions, and as well on application satellite, because now you show that they will be sensitive to radiation damage. So is there a program to fund instruments that are going on these various vehicles?
That is certainly, I don't know the specific programmatics, but that has certainly changed a lot. So instrumentation on the ISS, for example, is much more common, but also there have been missions. You know, we sent a radiation detector to Mars as part of the spacecraft that took Curiosity, which provided huge amount of information. In fact, we had solar storms that hit during that time. We also have the radiation monitor that's on the LRO, the Lunar Reconnaissance Orbiter, and that's provide a lot of information. But I do think this will, in order to truly understand these environments, that has to continue to happen. There has to be more and more radiation detectors. Because the thing that we've come to understand is how much we don't understand. As we go to these farther and farther environments, the physics has changed. Even curiosity and how the solar wind and coronal mass ejections have changed, New Horizon, as it's reached out there, that environment is so much more different than we could have ever imagined. Yeah.
Very nice talk. I would like to comment on the importance of knowing the conditions of the so-called planetary space weather in different locations in the solar system, because there are two aspects, to my opinion, of the planetary space weather. The one is the rigorously speaking scientific one. We need to know the phenomena that take place, for example, when a solar energetic particle flux hits the atmosphere of Venus or of Mars, or the aurora of Jupiter and its variability with solar activity, or the plasma from Geo satellite, and all this stuff. And the other part is the technological aspect. We need to know the conditions of planetary space weather, for example, around a planetary body, to both protect our spacecrafts, but also to interpret correctly the measurements that we get. And a classical example is the passage of comet Siding Spring from Mars.
Right.
So my question is, do you think it is sensible to have a basic, small, economical, let's say, payload, space weather payload on board of every planetary mission in the future?
I personally think that's a great idea. I mean, I'm hoping that this is one of the, well, there's sort of a toss-up. I mean, one of the issues is when you deal with those types of energies and particles, the easiest way to deal with them is mass, and of course that's a problem. However, having said that, there's been a lot of progress made in dealing with that, in putting things in the context of small sats and CubeSats. So I think that's a great idea to have small, compact space weather packages that can then be taken to other bodies. Because again, we're always surprised by the environment wherever we go. We have models which always have limitations and can never truly tell us what's really happening. So I think that's a great idea. Because we've certainly seen lots of things that happen, things we've learned from Venus Express and other missions about what happens when the solar wind interacts with the atmosphere, creating, its own kind of ionosphere and its own induced magnetic field. These are things that we definitely need to understand very well. So I think that's a great idea.
Okay, any questions to any of the speakers from the afternoon? Or returning the question on small pieces of equipment on all missions to the other speakers? Yeah.
Yes. This is actually an idea that has also been brought up in the context of the Galileo spacecraft. So there's a science team that is discussing whether you should put radiation sensors on all of the Galileo spacecrafts, which would make a lot of sense.
Yeah, I think that's great. I mean, we've certainly, radiation, particle sensors, and certainly magnetometers need to be on everything, I think. Yeah. But,
What was it? The scientist has wishes, and then it's the money which counts?
Exactly, yeah.
Okay, that was
Thank
not
you.
the best last words, but... Okay, I thank all the speakers and also the audience for being here. And